Okay. Hi, everyone. Welcome to the Sea Level Rise seminar. We're happy to have Dr. Tasha Snow today. She's a postdoctoral fellow in the Mines Glaciology Laboratory at the Colorado School of Mines, where she's working on ice-ocean interactions. She earned her PhD from the University of Colorado, Boulder in 2021, where she focused on cryosphere remote sensing and glaciology. And she earned her master's degree in marine science from the University of South Florida in 2014, and a BS in oceanography from the University of Washington in 2007. And her title today is "The Heat is On: New Applications for Thermal Infrared Imagery in glacier-ocean systems." So.
All right. Thanks, Patrick. And thank you, everyone, for having me today. Let's see if I can get this shared. All right. How does that look?
Yes, looks good.
Good. All right. Awesome. Great. So, yeah, here are some of the funding organizations. We'll just recognize those really quickly. I'll be talking to you a bit today about new applications that we've kind of designed for thermal infrared imagery, looking at for glacier ocean applications. And to start, I'll be giving you a bit of a background on ice-ocean interactions in Greenland and Antarctica. And then I'll be talking about 3 different projects that we've had demonstrating new applications for thermal infrared. And before I get started, I want to recognize all of the collaborators that have helped me on this. This has been a huge undertaking with people across the United States and the globe. So lots of great collaborators who are part of these projects. Now, to get us started, I know y'all are very familiar with sea level rise, but just for a little bit of background, the Greenland ice sheet obviously contributes 1/4 of total sea level rise each year, and about half of that loss occurs at the outlet glaciers that are shown here by the blues and purples because of the relatively fast moving ice that comprises them. So most of that loss is coming from these blue and purple areas around Greenland. In Antarctica, all of the loss occurs at its outlet glaciers for the most part. Now having problems turning the slides here. Okay. Hopefully you can't hear that beep. So in Greenland, kind of a history of our understanding of how change really began to set in Greenland is that in the late 1990s, Jakobshavn Glacier, which is shown here, began to thin and retreat rapidly. And so this is a satellite image, just to give you reference of Jakobshavn Glacier. You can see that this kind of like streaming ice here, this is the glacier. Can you see my pointer? Just to make sure, okay. That ice kind of ends here. This is the calving front, and that ice breaks off as icebergs. This is all floating ice and icebergs and sea ice, so that creates a melange that's floating on the ocean, and that's what all of this is here. And each of these lines shows the calving front for Jakobshavn back in history. So Jakobshavn retreated about 30 kilometers in about 110 years. So that's these dark lines. It kind of sat in the same point for 30 years, didn't really move too much. And then in 1997 began to thin and retreat rapidly. And it retreated about 20 kilometers over the course of the next decade. So really rapid retreat, it lost its ice tongue. And it was thought that this was caused by ocean warming that melted the ice tongue, but there weren't a lot of measurements at the time to confirm that. And then in the early 2000s, out on the southeastern side of Greenland, Helheim Glacier and Kindred-Ledswat Glacier also began to retreat and thin rapidly. And because all of these glaciers around Greenland these big glaciers were starting to retreat, we thought that this was caused by a regional trigger, which could be obviously atmosphere or ocean caused. And we believed that it was ocean triggered. And it wasn't until about 2008 when we finally gathered some historical evidence. This was work done by David Holland and others that implicated subsurface ocean warming in the retreat of Jakobshavn Glacier. So this was a really cool data set that used data from ocean or fishing trawlers that were taking ocean temperatures in the subsurface waters on the western side of Greenland. And what you can see in this map, these maps from each year, is that you see this warm signal that's kind of creeping up the western side of Greenland, and finally reaching Disco Bay and Jakobshavn in 1997. And that's when we began to see retreat. So there's good evidence that ocean warming triggered that there, but we really don't have this sort of evidence back in time around most of Greenland. And even now to this day, there are some records, some longer term records that kind of began around 2008, but we really don't have much in most locations around Greenland. To kind of give you a background of what these systems look like oceanographically, I'm sure many of you know this already, so I'm sorry for giving you the same background. But so around Greenland, you have polar water that sits at the surface. It's relatively fresh and buoyant because it's comprised of meltwater, both from the glaciers around Greenland and sea ice melting in the Arctic that's coming from south from the Arctic. And this water sits at about, from the surface down to about 150 to 250 meters. And then below that is Atlantic water. And this is relatively salty and warm and sits down below that polar water. And this is where we really care about a lot of heat getting transported to the glaciers around Greenland. Antarctica has analogs to these called winter water at the surface and circumpolar deep water at depth. Now, the way that this Atlantic water is often transported towards the glacier is where it comes in at depth, it melts the glacier at the grounding line, mixing relatively fresh and buoyant water into the water column, and that, because it's buoyant, rises towards the surface as a plume. And then that escapes away from the glacier at the surface. And this is called glacier-driven circulation. This is dominant during the melt season in summertime when you have a lot more melting, creating that circulation. Another way that you can transport heat towards the glacier is through wind-driven intermediary circulation. And this occurs when you have winds blowing along shore just off the coast. This pumps water in at the surface and out at depth. And then when those winds reverse or weaken, then it pumps water in the opposite direction in the fjords right in front of the glacier. And so you get this oscillatory motion in the circulation. So it's not really clear how much heat, how much Atlantic water that actually brings to the glacier front. But it flushes the fjord and pushes about an order of magnitude more water into these areas than the glacier-driven circulation. So it can potentially move a ton of heat towards the glacier. And this is most common in non-summer months when we have higher winds. Now, the work that I'm going to show you today is based on the premise that we don't have many measurements of the ocean around Greenland or Antarctica. And so how can we use remote sensing to better understand the amount of heat that's being transported there? So I'm using remote sensing, specifically sea surface temperatures from satellites, to expand our ocean records in space and time. And some of the satellites that I'll be showing you records from are in the NASA Earth Science constellation. They're from Aqua and Terra right here that have the moderate resolution imaging spectroradiometer on board called MODIS. I'll also be showing you some records from Landsat 7, 8, and 9. And now into the fun results and work that we've been doing. So this is the 3 different projects that I'll be talking to you about today. We'll be talking about sea surface temperatures and how they can provide a proxy for surface and subsurface water temperatures in southeastern Greenland. I'll be combining thermal and optical imagery to detect an unrecognized mechanism driving warm Atlantic water towards Helheim Glacier. And we'll use thermal infrared to detect ice features and warm plumes at the ice-ocean interface in Antarctica. So we'll move south at the end. All right, so starting with the first project, this is a project that was published in the Journal of Geophysical Research Oceans last year, so you can check that out. This work was done as a case study at Helheim Glacier, and this is Helheim Glacier to kind of give you reference of what you're looking at here and what this area is like. Helheim Glacier is over here on the left. It's flowing from left to right. And this is the calving front right here. Sorry, this is the calving front right here. And the icebergs break off and create this melange. So this is all floating ice. And just for reference, the ice front here above the ocean is about 30 stories tall. So this is about equivalent to the highest building that tower that you have in DC. And it's much thicker beneath the ocean, but that's kind of what the ice front, the size of the ice front here. And Helheim Glacier is really interesting because it has retreated a lot in the recent past. You can actually see this kind of bathtub ring right here along the mountains. Helheim Glacier was much thicker only a few decades ago. And so it's experienced a lot of retreat. It's a really interesting place to be doing this work. And I'm doing work here because there's also quite a few oceanography records that are longer term. And there's been sea surface temperature work that's been done here. So in general, sea surface temperatures aren't widely used around Greenland, but these two projects and a few others have used them in different ways with conflicting results. So on the left, this paper by Ian Howitt and others showed that offshore sea surface temperatures were warmest in summer 2003 when the southeastern Greenland glaciers began to experience their highest retreat rates. And so they made the connection between offshore sea surface temperatures and inshore ocean warming potentially, but that connection wasn't actually really proven. And then in the paper by David Sutherland and others in 2013, they showed that sea surface temperatures don't correlate with temperatures down to more than 250 meters, which is where all this Atlantic water sits. And so potentially sea surface temperatures aren't useful at all for understanding how much Atlantic water and how warm that Atlantic water is getting towards the fjords and glaciers in Greenland. What I'm gonna point out here though is that these projects use summertime sea surface temperature, which I'll show you in a moment why that's problematic to use summertime sea surface temperatures alone. Now in the work that I'm going to show you, we have 3 data sets. I'm using MODIS sea surface temperatures from the Aqua and Terra satellites, have 2 products each, which is the daytime and nighttime products. And then because sea surface temperatures are sitting at the measuring the interface of the ice or of the ocean and the atmosphere, I wanted to see how air temperature and ocean temperature contribute to that. So we compared to subsurface mooring temperatures at the fjord mouth at Helheim Glacier to give us that ocean temperature comparison, and ERA 5 air temperatures. These are reanalysis data for the air temperature comparison. Now, so to give you a little bit of background on what actually sea surface temperatures are, this is a schematic of what they're actually measuring. So thermal infrared measures the top few microns of the ocean surface, and that's called the sea surface temperature skin. And the skin effect means that those temperatures are slightly cooler than the rest of the water column below them. There are 2 different kind of dimensions to how sea surface temperatures change in comparison to the water, or how the water column changes and how what sea surface temperatures measure. And one of those dimensions is seasonality. So in wintertime, the water column is homogeneous from the surface down to depth. So this is depth along the y-axis and temperature increasing to the right. And because the sun is not up during wintertime and winds are relatively high, you get that homogeneous water column. So sea surface temperatures are potentially measuring down to pretty deep in the water column. But in summertime, you have the sun coming up, warming the surface. You get a surface thermocline, or a gradient in temperature through that's sharp through depth. And so the mixed layer is quite a bit shallower, and the sea surface temperatures may not reflect as deep in the water column. Now you also have a diurnal effect. So at nighttime, you get a lot more mixing because the sun is down and the winds are a bit higher. But in daytime, all of that changes, and the input from the sun creates a diurnal thermocline that can make the sea surface temperature very different than temperatures even a few centimeters to a meter deep. So you can imagine the sea surface temperatures, what they're measuring in the water column changes very drastically throughout the year. And this is really important because MODIS takes 12 to 18 scans per day, and as I mentioned, is binned into a daytime and nighttime product. And because polar regions experience a polar winter where it's all nighttime for 24 hours, and polar summer where it's all daytime for 24 hours, you get these scans that all of these scans per day are binned into a daytime product in the summertime, biasing that product towards summertime. So as I showed in the schematic just a moment ago, if you have something that's representing summertime sea surface temperatures, and daytime, they're probably not measuring deep in the water column. Whereas your nighttime product will be giving you a measurement that's much deeper in the water column. So all of those projects that use these summertime, daytime products are definitely only measuring the surface ocean with their sea surface temperatures. All right, so kind of digging into the project that we did here, this is Helheim Glacier, or this is just offshore from Helheim Glacier. The circulation here is such that the Erminger Current comes from the North Atlantic, bringing warm Atlantic water up towards Greenland and along the coast towards the southeast of Greenland, just along the continental break. And the East Greenland coastal current brings the East Greenland coastal current brings polar water down from the Arctic along the coastline. And it's only about from surface down to what I said, 150 to 250 meters. The Atlantic water offshore is from surface down to depths much deeper than we care about. So that's a pretty homogeneous water column. And zooming in to right offshore from Helheim Glacier, this is the Erminger Current. The dotted line is the East Greenland coastal current path. This is bathymetry showing you some troughs here that are right offshore from Helheim Glacier. And this is a composite of sea surface temperatures from 2000 to 2016 that show that the average across that period of time. And what's really interesting is that you can see these warm splotches kind of trailing in on the right-hand side of these troughs. So water is turning in from the Erminger Current onto the continental shelf of these troughs. This one, it continues on, that water continues on underneath the East Greenland coastal current in towards Sermelik Fjord and Helheim Glacier. So that Atlantic water is creeping in underneath the East Greenland coastal current. But you can actually see where these troughs are located based on sea surface temperatures, which is, I think, is fantastic. It's really cool.
Tasha, we have a question in the chat. Sorry to interrupt.
Sure.
So Allegra is asking, does the temperature profile change if there's been strong melting and a surface pressure layer?
The temperature profile change just in general with the polar water and Atlantic water, or sea surface temperatures?
You have a convergence of salty North Atlantic water and fresher melting water. Do you have a strong halocline, and how does that influence your temperature profile?
So are you saying just right here offshore, kind of?
I mean, in general, like if you're going to use SSTs for proxy and you have a really strong halocline, that can effectively change like the thickness of the water that you have to heat up.
Okay, you're asking, yeah, absolutely. So we worry about that mostly in the East Greenland coastal current. The Atlantic water, like I said, is pretty homogeneous. Atlantic water from surface down to deeper depths, so that you can get meltwater out there, and that does impact sea surface temperatures. But on average, usually that's pretty well mixed within the Erminger current. The East Greenland coastal current, absolutely. If there's a lot more meltwater that's entering the East Greenland coastal current, if it's not well mixed, that's going to really change your sea surface temperatures and limit the relationship between sea surface temperatures and what's below it. It's going to be minimized if there's a lot of meltwater sitting at the surface, for sure. Cool. All right, so for the project that we did, we actually looked at the East Greenland coastal current as an end member for polar water. We looked at the Erminger current as an end member for Atlantic water to see what the temperatures of those are. And then we looked at this green shelf trough box right along that trough to look at the temperatures of the water that are kind of getting up on that trough towards Seasonality Fjord and Helheim Glacier, and potentially continuing on at depth. And that's going to be the mixing region that we compare to the subsurface mooring temperatures that we collect right here at the mouth of Seasonality Fjord. We also do a comparison between the Erminger current temperatures we take and the mooring that's shown here just south within the Erminger current to show a relationship between showing how well mixed that is, how those sea surface temperatures compare to that mooring. And these are the records that we collect from this. The shaded colors are daily measurements, and the monthly measurements are the thicker line there. And we're interested in understanding how much of the variability is attributable to air temperatures versus upper ocean temperatures. And so first we do a comparison with air temperatures. So to give you reference on this figure, this is air temperature increasing to the right along the x-axis and sea surface temperature on the y. Wintertime measurements are in purple, and summer are in teal, spring and fall are in gray. And these black dots are showing you month by month how this relationship changes. This is at the shelf trough, but these relationships are really similar in the East Greenland coastal current and the Erminger current as well. What you'll notice is that there's a strong relationship in the summertime, a nice linear relationship, but in wintertime that goes away. So sea surface temperatures are pretty tightly coupled to the atmosphere in summertime, but not in winter. So that begs the question, what is driving the sea surface temperatures in wintertime, right? And we expect that to be the ocean, and that's what that turns out to be. So here's sea surface temperatures. We compare those to that ocean mooring that's down in the Atlantic water by the fjord mouth. And we see a nice linear relationship in wintertime between sea surface temperatures and the mooring temperature, and almost and no significant relationship in summer. And that's because, again, there's less solar radiation, there's higher winds, so that Atlantic water coming on shore is better mixed, and the sea surface temperatures relate to much deeper ocean temperatures in wintertime. Now, what we're really interested, so this gives us a great proxy for wintertime subsurface temperatures in this area, but what we're really interested in is also seeing that year round. And so what we did is we created an adjustment for the sea surface temperatures that accounts for that variability that's tied to the atmosphere in summertime. And we used an ordinary least squares regression with a monthly interaction term and removed that. And what we did is we went from having this green record, which is the original sea surface temperatures, to the adjusted, which is the dotted orange. And we have the standard error that's the shading here. And what you'll notice is if you compare this to the mooring record in black, this actually reproduces the mooring record really well in many of the summer measurements that we have. And so we have a better proxy in wintertime than in summertime, but on average, it's about 0.7 degrees root mean square error. So we've created a proxy that in this specific location gives us a subsurface proxy for what is entering Surmulink Fjord towards Helheim Glacier. And so what this is actually doing is giving us an upper ocean temperature. So we did this for the Irminger Current and East Greenland Coastal Current as well. And so that will give us reflect down to wherever in the water column this water is homogeneous. So that in the East Greenland Coastal Current, that should usually be about down to 150 to 250 meters. In the Irminger Current, it'll be much deeper. And that is reflected in the mooring records that you can see here. So we've put the mooring records on top of those. And the first thing that I want you to notice is when we were thinking about offshore sea surface temperatures earlier and how well offshore temperatures compare to inshore temperatures, what you'll notice here is the Irminger Current doesn't always look like, in yellow, doesn't always look like the orange line here, the shelf trough area. Sometimes it's more similar, and sometimes the shelf trough is more similar to the East Greenland Coastal Current. And we actually, I'm not showing this today, but you can look at this in the work that we did. This is actually varying with how wide the East Greenland Coastal Current is and how much that East Greenland Coastal Current is transporting. So when the current is wider, it's diluting this water as it crosses the continental shelf and making it a much cooler temperature than when the current is more narrow. So offshore Atlantic water temperatures don't reflect the Atlantic water temperatures that are making it into Surmulink fjords. That's an important point. The other point I want to make is looking at these records, the warmest temperatures that we see in all of these records occurred when thinning began taking place and a lot of retreat in these southeastern Greenland glaciers. So it's likely that ocean temperatures played a large role in the retreat of these glaciers. Giving you an overview of all of this, we have a new sea surface temperature processing method that provides estimates of the upper ocean temperatures. The adjusted shelf trough sea surface temperatures can be used as a proxy for subsurface water temperatures feeding Surmulink Fjord. And offshore temperatures don't necessarily predict inshore temperatures, so there's variability in that dilution. Great. So second project that I'll talk to you about today. This is a project that's been submitted, or it is about to be submitted to Earth and Planetary Science Reviews. It's been in review, and it is associated with that wind-driven intermediary circulation I mentioned a few minutes ago. This actually, this project came out of an accidental observation that I made when I was just looking at some imagery, some striking imagery from near Helheim. This, just to give you reference, is a time series from 2013, February 27th to March 1st here on the right. And I'm showing these wind vectors to show what direction the winds are blowing. And for reference, this is the coastline in this image looking down. This is Surmulink Fjord. This is Helheim Glacier. And this is the East Greenland Coastal Current, covered in sea ice, which is flowing. This is all flowing towards the south from the Arctic. And there's that warm Atlantic water offshore. Now, when the winds are kind of blowing in their prevailing direction from the north east towards the southwest, that's creating a downwelling circulation at the coastline that drives that water in towards the shore at the surface and out at depth. And then you get the opposite when the winds slacken or blow in the opposite direction like they do here. So you have upwelling taking place during this. And what you'll notice is that you have this really interesting feature crossing the East Greenland Coastal Current during the upwelling. And if we look at thermal infrared, we can actually see that there's a decent amount of Atlantic water within this intrusion that's cutting across the East Greenland coastal current, and that it's actually occurring along the right side of this trough. So you have a the warm Atlantic water kind of coming in as an entire packet of water. So this is this is Atlantic water that's being upwelled all the way to the surface along the trough. And this is being stimulated by upwelling along a bathymetric trough. And when we look at what caused this was actually triggered by a cyclone that was passing by. As the cyclone passes by, it creates downwelling along the coastline. And after it passes, on the back end side, the winds reverse, and that creates upwelling, which triggered this intrusion. And we actually have this amazing sea surface temperature record of this to be able to look at it in space and time pretty intricately. So this is the records that we have. And so once it's finished, so if we concentrate on a few days before this intrusion happened, there's no intrusion here at all when we have downwelling on the coastline. But like 5 o'clock in the morning on March 1st, we start to see the intrusion grow up the right-hand side of the trough. This is at 6:45 in the morning, and by 12:55, this is fully developed intrusion that has moved several tens of kilometers. And so this is extremely rapid event. And it's documented around the world that this can happen, but it's never been observed in remote sensing. And what remote sensing adds to this is now we can have a spatial picture of this to better understand the mechanisms that are driving it. We have captured multiple intrusions. Here's just a few examples of those. And we've compared, we've looked at how those intrusions have impacted the ocean temperatures at the mooring that I showed you before within the Atlantic water at the fjord mouth, as well as mid-fjord, both at about 250 to 300 meters. And what we've done is created a composite where when the winds shift from downwelling to upwelling favorable, we've put that at the 0 point here, and then taken 59 different intrusions and averaged those together. And what you'll notice is that when that shift happens, there's a spike in temperature in both the fjord and out on the shelf. And what's really interesting is that even though this is a cyclical pattern, the water temperature doesn't return back to what it originally was. So this is a persistent temperature change that is being caused by this water going, intruding during upwelling and not being pushed back out during a downwelling event. And what's even more interesting is, as you can imagine, this is being triggered by upwelling over a trough, and there are lots of troughs along the coast of Greenland. So when this cyclone passed, we actually saw near synchronous intrusions across the region. You can see those here at some of the troughs. So this is potentially a mechanism that is bringing a bunch of heat towards Greenland and towards the glaciers. So if we have a lot more cyclones that are passing by, or much more upwelling events, then we're likely to be transporting a bunch of heat towards these glaciers. So kind of to sum this up, this is an unrecognized mechanism driving Atlantic water towards Helheim Glacier, and it's caused by coastal upwelling along a trough, often following a cyclone. It produces subsurface water warming on the shelf and in the fjord, and it may be important for heat transport towards other glaciers around Greenland. Now, to kind of end this talk, I wanted to move down to the south to Antarctica and talk about some of the exciting research that we're doing there now, looking at persistent polynyas and basal channels, which I'll describe here in just a second. But we're moving down to Antarctica. This is again ice velocity. You can see in the blues and purples that these giant ice shelves kind of take up a lot of the area around Antarctica. But if you focus over here around the Amundsen Sea, this is Pine Island Glacier and Thwaites Glacier, which you may have heard about in the news. These guys are pretty bright colored. They actually account for 37% of Antarctica's mass loss. So this is where we're gonna kind of travel to here for just a few minutes.
We have another question in the chat.
Okay, cool.
Gavin. He says, does the wind change move the sea ice in ways that increase the intrusion?
Yeah, so that's a really good question. We haven't really dug into that specifically. So this is so localized that it's not really, and it's moving in the direction towards shore, which is opposite of the winds. So this is this jet of water is definitely not created by sea ice moving out of the way from it. In that respect, this is upwelling that's causing this water or the sea ice to diverge. But certainly the sea ice coming offshore is definitely associated with downwelling and the winds causing that, or sorry, upwelling. But we don't think that, yeah, that this intrusion, the surface expression of this is associated with the winds. Cool. All right, so this Antarctica project is being worked on by a big group. It's in association with the International Thwaites Glacier Collaboration, as well as some NASA ROSES funding that we just got last year. And it's looking at basal channels and persistent polynyas, as I mentioned before. And this is just to give you a little bit of background on what those are. So similarly to Greenland, circumpolar deep water comes onto the continental shelf. It melts at the base of the ice, and that creates a plume that rises towards the surface. Since we have ice shelves here, the base of the ice, the plumes will find topographic highs in the bottom of the ice shelf and follow those, and tend to follow those over and over and over again. The plumes are turbulent, so they entrain warm water in them. And so as they rise, they incise the bottom of the ice shelf too. So these areas begin to form channels where these plumes are going to the same location over and over and over again. And then these basal channels begin to funnel those plumes all the way towards the surface in the same location through time. Those plumes can exit out away from the ice shelf at depth, or if they're buoyant enough, they can rise to the surface at the ice front. And since they're warm, if there's sea ice there, they will melt, potentially melt out the sea ice and create what is known as a persistent polynya. So it's an open water area surrounded by sea ice. And these tend to be circular, and they occur in the same location multiple years in a row because they're at the ends of these basal channels, which are relatively stable features. So these are occurring only seasonally though. So sometimes whenever the melt season is, that's when these plumes tend to get to the surface, if there is enough buoyancy in them. Now, for this project, we're looking at a bunch of persistent polynyas around Antarctica, but today I'm just going to focus in, we're starting with a case study at Eastern Thwaites, which is right over here where this black box is. And this is a satellite image looking at that area. So our goal is to investigate the persistent polynya variability and mechanisms driving that variability. To give you a reference of what they look like, this is Pine Island Bay, Pine Island Ice Shelf, Eastern Thwaites Ice Shelf, and this is sea ice. So this is the ice that's formed on the ocean that's floating there, and this is the land ice. And I'm pointing out basal channels and a persistent polynya, which I will zoom in here with Landsat. There is a surface expression of the basal channel here and the persistent polynyas. So this is what these look like. The red is the grounded area for this ice shelf. So this is what we're trying to identify how these polynyas vary in time. And we're trying to automate that using a cloud-based workflow. The cloud-based workflow is meant to be collaborative and fully reproducible and shared openly. We've done it in AWS using Python and Jupyter Hub, and using a bunch of these data ingest structures, processing and visualization libraries. And the data that we're using is from Landsat, MODIS, and Sentinel. And when we put all of that together, this is kind of the output that we get. we're basically just creating shape files of the locations of these persistent polynyas in each of the images that we have. So that's the blue right here outlining that. And to automate this, we're also adding physics featureization. So we're adding information into a machine learning algorithm that tells it that these polynyas should be located at the end of a basal channel, which we know the locations of. It should be located at the edge of the ice front, which we can detect from image to image. And so we put all that together to automate this. And some of this work is being done by several people in our group. So I'm gonna brag about the undergrads and grad students working with me on this project now. Ojin Lee has done a bunch of labeling for this work for the neural nets, and Michael Field is now a graduate student, but was an undergrad at Colorado School of Mines. He's now moved on to work with Mickey McKee in geostatistics at University of Florida. And Ojin is at Columbia University. So they've been working together to produce this neural net that detects the ice front. And that will be fed into this physics featureized segmenter that is being produced by Ellie Abrams, who is a PhD student in statistics and astrophysics at Berkeley. And so we're collaborating with her to create this segmenter. She's fantastic. I cannot highly recommend more working with people in data science and statistics. It's been just incredible to work with them and to see some of the cutting edge work that they can do for our field. So she's still working on that, but the output from that gives us something like this, where we can see the areal extent of this polynya through time. And the areal extent is represented here by the size of the circle and the color of the circle here. So this is from 2013 to 2021. And the white here, just so you have a reference, is where we can detect the polynya because there's landfast ice. You can see that polynya in there. And on the right-hand side is the blue is when you cannot detect the polynya visually because there's melange or open ocean. Down the road, we'll be able to use thermal infrared to detect where these outflows are, even when there isn't melange, but for now, we're just using visible imagery. Now, just kind of looking at the results here, you can see that there's quite a bit of seasonal and interannual variability, both in the areal extent as well as the longevity of this polynya. So how long this polynya is open from year to year. So it can be open anywhere from 1 month to 6 months each season. And we think that both the size and the longevity of the polynya are related to how much basal melting is happening beneath the ice shelf, especially early in the season. And then ocean stratification is also coming into play later in the year. As the ocean stratifies, it prevents the plumes from rising to the surface and creating these polynyas sometimes. So we're teasing out this interplay between those two causes, but we're hoping to be able to use this understanding of this polynya at the surface where we can remotely sense it, where we don't have many measurements from the ocean, in situ measurements. We can be able to use the remote sensing to better understand what's happening beneath the ice shelf without actually having to be there. Now, some more work that we're doing within this project is to look at the relationship between thermal infrared and surface elevation. So the surface expression of these plumes, which is really cool, using ISAT-2. And the work that I'm showing you here is pretty rough, but this is work that was done by 4 graduate students and myself over the course of 3 days in the ISAT-2 Hack Week. And so this kind of shows you some of the incredible work that can be done when we do some open source coding and training with a bunch of people, several people who have never worked with ISAT-2 before, some who are newer to Python. This is kind of the work that we can create in just a few days. And so this work this project is something that we're going to wrap up probably in the next month or two that we're continuing on with. And so if you want to know more information about the Hack Weeks, please ask me more. Other work that we're doing is that I'm producing and ground truthing a fused multi-platform sea surface temperature data set at the Polynias in Antarctica. So I'm producing Landsat sea surface temperatures. There is no product for that, so I'm creating them myself. And fusing those with MODIS and Sentinel data, which is lower spatial resolution, higher temporal resolution. So we really want to match those two kinds of data sets together to be able to see these polynyas in high spatial detail as well as the high temporal detail. And some of the work that's also been done here is to compare and ground truth those sea surface temperatures using seal tag ocean measurements. And so this is work that's been done by Elena Savage, who's a grad student at the Colorado School of Mines. And she just submitted this paper to IEEE, where she showed that warm seal tag measurements were associated with warm thermal measurements that were being taken in wintertime from Landsat and MODIS. And so these warm plumes are where seals like to congregate in wintertime. And so we have a bunch of measurements of them, and thermal is corresponding to what we see at depth. Now, what's really interesting is that we can see finer detail in Landsat up on the top here than we can MODIS. But Landsat actually isn't taking any measurements, any imagery in wintertime for the most part back in time. And so part of our push here is to say that we'd really love Landsat thermal, especially to be collected in polar winter when the sun is down, so that we can have records of these polynyas and other thermal features back in time. Because right now we only have a few measurements taken in 2019. And that makes it hard to observe these in wintertime. That acquisition is hopefully happening now, but yeah, this is one of the problem spots for Landsat. And this is kind of an overview of all of that work put together, sea surface temperatures and the ice fronts being pumped into the physics feature ice segmenter to get persistent polynya variability. But before I close, what I'd love you to notice here is this box over here on the right. We are collaborating with 2I2C, which is an international interactive computing collaboration, who has stood up a Jupyter hub for us to work in the cloud. And we've just gotten funding to stand up one of these clouds for NASA cryosphere communities. And so we're going to be at a few different workshops that are already within the community at WACE, FOGS, if you're familiar with those, and AGU. We'll be inviting scientists to join the cloud computing environment and be able to use this. And it's a simple, intuitive, and cost-effective system. It's built and developed for cryosphere scientists, and it will have new tools that will be built for us. On this system, you can teach classes for cents per student per semester, and this kind of levels the playing field for students who may or may not have the resources to get good computing platforms on their local computer. You'll also be able to read in data and have compute times that are sometimes 2 orders of magnitude faster than on your local computer, because you can read them so much faster in cloud optimized formats. So if you're interested in learning more about this, please ask me later about more information for that. So to kind of wrap up, I talked about a new method for deriving upper and in some locations subsurface ocean temperatures from sea surface temperatures. In Southeast Greenland, found a mechanism for rapidly transporting warm ocean water towards Greenland along troughs. And we have ongoing work looking at those polynyas and how the ice shelf evolves with that and impacts ice shelf stability in Antarctica. So this, hopefully I've convinced you that thermal infrared imagery can be a really useful tool for many applications around the ice sheets in ways we haven't historically used them. Thermal infrared data sets are spatially comprehensive and can take our records back 4 decades, and we'll continue on with Landsat that has just been launched. What I've shown here in these methods is that they're super complementary to our sparse field observations, and pairing them is crucial for getting at the mechanistic understanding of these incredibly complex ocean systems. So with that, I want to thank my funding sources and take any questions.
Thanks, Tasha. It was great. We have a question from Chris in the chat. Chris, I don't know if you want to unmute and ask it. Otherwise,
yeah. Great job, Tasha. I'll even click the camera on so you can actually see me. Basically, we are in the process of getting the USGS to take all of the Landsat extended acquisition plan scenes and get them into regular acquisition. For Greenland, I just found out yesterday that they have implemented that, and now we're in the process of trying to implement extended acquisitions for Antarctica that will try to do exactly what you're hoping we will have, which is more thermal data in more places. The reality was there during COVID, they were kind of shorthanded, and so even though we had a plan together, it just didn't get implemented. But now that Landsat 9 is up, we're getting back to it. This is Ted Scambos, Mark Fonstock, and myself have been pushing for this. So look for more data soon, and we can talk more offline. But I did want to share that view of Helheim that we put together in 2019, just because the OMG flight over the Polinia off the front of Helheim is just such a spectacular image. There's actually drone footage, probably from the same people, that side view that shows the water upwelling and pushing the bergy bits away.
Yeah, so I'm really hoping we can capture that in ISAT too at some point.
There could very well be an elevation difference from the top of the plume to the edges. The Helheim calving so quickly, you lose the plume under the recently calved ice. The other little tidbit that I can't prove, but I will put into your thinking cap, which is that prior to 2010 at Helheim, you really don't see those persistent upwelling Polinias off the ice front, but you sure do with the more regular acquisitions during Landsat 8. So it's hard to say how far back this phenomenon developed, but it seems to be recent.
We're gonna have to look into it more.
You bet. Happy to talk more.
Always. Gavin?
I think Chris and Suzanne were ahead of me in the line. So.
Okay, so this is Chris Little. Thank you, Tasha. That was really interesting talk. So I wrote out one in the text, but basically I'm wondering, you've got these kind of three different examples of the relationship between SST, subsurface offshore temperatures, and temperatures in the fjords. And it seems like there are times when those things are correlated, or the fjord temperatures are correlated with the offshore water, and times that they're not. So I was wondering if you had any insight into, under what conditions these things are related. Like, are they obviously, subsurface seems to be related over very long timescales, and is it related to, the timescales, or is it related to the details of the forcing that's causing the coupling that's driving the ocean, essentially?
Yeah, so at least if you're referring mostly to Helheim, the how closely coupled those are, the offshore temperatures to the inshore temperatures, we've found in and you can read the paper that I showed earlier. We found that the East Greenland coastal current width, so the transport within the East Greenland coastal current is what changed that. So if the East Greenland coastal current is wide and transporting a bunch of polar water within it, then there was more dilution of the water across the continental shelf. And so offshore temperatures were not similar to what was inshore at depth. But when the East Greenland coastal current is more shallow and narrow, they were much more closely coupled. And so you have that warm Atlantic water kind of already intruding closer in towards shore and just has a shorter distance to travel, and doesn't get diluted as much. So it should be associated with how wide the East Greenland coastal current is on average.
And with the intrusion event, was that related? That's one where, and that's not related to the East Greenland coastal current, or?
So it is. I think we actually didn't look at these projects in tandem, which I think would be a really interesting thing to do. The East Greenland coastal current does kind of put a lid on these intrusions. So the wider the East Greenland coastal current is, the harder it is for these intrusions to develop. At least at the surface. Potentially down at depth, they're happening. We can't see them from remote sensing. But certainly I think
So are we only seeing the intrusions when the conditions are ripe for that to occur?
Yeah, and generally
not just the winds, but also the ocean state?
Yeah, so theoretically, we can't prove this. Theoretically, based on the mechanism that we're seeing, these intrusions should happen every time there's upwelling. But the East Greenland coastal current would probably be preventing the surface expression of that, because ocean stratification at the surface can prevent those intrusions from penetrating all the way to the surface.
Okay. It is complex.
It is really complex, yeah.
Yeah. Thanks a lot.
Yeah.
We had a question from Susanna.
Yeah, Tasha, thank you. That was a very nice seminar. I'm not from this field, so
yeah,
I learned a lot today from you. I was just wondering about the seal. Why would you use a seal to make measurements instead of something passive that you can control? Or I wonder if that also has another dimension of a biological project or something. I was just curious about that.
Yes, there are biological projects coming off of that. I mean, we're using the seal tag data for studying seal behavior as well. But that's a really great question. And that the seal tag data is being used because shipboard measurements are something we can control, but it's hard to get into a lot of different places, and the ship can only be there a couple months out of the year. Seals are there year round, and these seal tags, the CTDs that sit on their head, stay attached for about 9 months. So we can get measurements from basically the summer when we put them on until, through the winter until sometimes fall. So we get year-round measurements from them. The reason why we have moorings in the area. You can't have moorings very high in the water column because Antarctica is just harsh and icebergs like to destroy moorings. So moorings that are very high up in the water column are pretty much non-existent. They don't last very long. And yeah, so I mean, that's kind of the main issues that we have. We have ocean gliders there sometimes in wintertime. They can't come as close to the surface, but a lot of times they're not getting close to the ice front of these glaciers and as close as we needed to, because this is literally within a kilometer of the ice front, because the ice front is such a hazardous place for gliders. So seals will be diving wherever they want to be. We can't control them, but we get thousands of CTD measurements through the 9 months that a seal will have its CTD. So we get a ton more measurements than we could get from a ship or anything else, and for larger portions of the year. So we can't control them. The measurements are a little less accurate, but the sheer quantity of them make it totally useful. Thank you for that question.
I think you showed a picture of one of the Pine Island birds, maybe B34, and B34 stands similarly to Helheim, so high up out of the water that it casts a shadow that you can actually use to estimate the height especially on Landsat ascending passes. And that height translates into the thickness of, 600 meters. So that gives you, Suzanne, that gives you an idea of how deep these keels are that would drag anything out of their way as they shatter. So
we lose a lot of moorings that way.
Yeah. Great picture.
Gavin.
Hi, yes. Yeah, great talk.
Here.
So my questions always come down to how do we deal with this in a modeling framework, right? So these are all, relatively small scale features, right? A few 100 kilometers at most, but they all seem to be very important. And so,
yeah,
how should we, how should we think about these things? How should we think about implementing it or making sure that what we have kind of fits the net impacts that you're seeing? I mean, you've got, almost all of the, well, okay, so maybe this is the question. A lot of the pictures you showed had a very two-dimensional view of what was happening underneath the ice shelf or the floating ice.
Mm-hmm.
And so there's been some work on developing two-dimensional kind of parameterizations that kind of that just kind of estimate what would happen underneath the ice given a profile at the front. Is that but perhaps not sufficient? I mean, is that going to capture like the zeroth order effects of these things, or are we really? Is it just going to be totally hopeless unless we can get like kind of high resolution sub ice shelf 3-dimensional circulation models going?
Yeah, I mean, I think in general, based on the system that we have, I'm going to have two answers for this. Based on the system that we have, I think there are parameterizations that we can put in here. There has been modeling studies on this, like these intrusions in Greenland. There have been models elsewhere, like at the Hudson Strait Valley. So I think that we can parameterize in some of our models based on the fact that we just know when upwelling is happening, this sort of thing should be happening. But I think what I would also plug in here is we've been doing a lot of work with machine learning and with the data scientists that I mentioned and some more groups, and we have this cloud computing environment. And I really think that the way of the future is pairing these big physical models to machine learning models that can really quickly get at these kinds of answers at the small scale without adding a lot of computation. And I know machine learning can kind of be a black box, but we're getting to places where we can, these black boxes are much more explainable. And especially now that we're getting into physics featureization, we can kind of tell the machine learning models what is important to pay attention to. So we aren't getting things like it making the decision for the wrong reasons, like we see often with machine learning, the right decisions for the wrong reasons. So I think that there's this, there's just much more, there's a lot of room for adding these statistical models and machine learning to what we already have and kind of pairing them to get the best of both worlds.
Yeah. Okay. Well, that's interesting. I mean, I often wonder, how well those kinds of approaches work in out of sample climates, right? So 2 times situ, where the East Greenland current suddenly looks a lot different, or where the sea ice is a lot less, or where there's a lot more intrusion of Atlantic water. Is it still going to be credible? I mean, those are interesting questions. But anyway, thank you very much for the answer. I think there's a lot to think about there.
Yeah, I think that's something that I'm wrapping my head around right now a lot, especially working with these data scientists. I think there's lots of ways their statistics can even just improve the computation in some of this and ways of making these models faster, which would make them better just in itself. But yeah, I love this question and like the opportunities that we kind of have moving forward now that, our computational ability is increasing rapidly. And our knowledge of these areas and the remote sensing measurements and the in situ measurements are all like kind of exploding. We have so many more data sets now. So I think there's just so much incredible work that will be done in the next decade.
Okay, thank you.
Okay, well, are there any more questions?